All right, in this lecture, we'll talk about index properties and soil classification and move on to talking about phase diagrams. So the issue that we're going to be dealing with here is that soil is composed of multiple different phases of materials, which is different from a bulk material like steel, which is really only like one solid component, right? Soil is a particulate material. It's composed of solid particles. But there's also liquid, usually water, although there could be other liquids that are in the soil, and gases, typically air, but there could be methane. In Southern California, we actually have places with quite a bit of methane in the ground. But anyway, that's beside the point for this lecture. All we need to really focus on here is that you've got these three different phases that are contributing to the soil composition. So solids, liquid, and gases. Okay, so one thing I'll talk about too are index properties versus non-index properties. So phase relations are actually not an index property because the water content can change, but it turns out that whether we call a soil a gravel, sand, silt, or clay depends only on the index properties, including the grain size distribution. So that's what's the distribution of different sizes of grains within this soil, and the Atterberg limits, which we'll talk about as well. Okay, so index properties are defined as ones that do not change even when you remold the soil. So let's say we go to a site, the soil's there, we want to get some soil samples to do some kind of laboratory testing. Well, if all we care about is the grain size distribution, what particles are in the soil, what's the percent of clay, what's the nature of those clay minerals, and so forth, then we can just go out with a shovel and dig up a bunch of earth and put it in a bag, right? As long as we're worried about shallow soil. A lot of the time we have to drill down to get to it. But we can get highly disturbed samples where the soil is completely remolded from its in situ condition, and then we can do those tests. We can measure grain size distribution, we can measure Atterberg limits, which is actually measure the stickiness of the clay content in a soil. So those are index properties because they don't change when the soil is remolded or you add water to it or something like that. The index properties stay the same. So non-index properties are also very important for us. Those are things like strength, compressibility, stiffness, water content, right? Those things are not index properties because if we go out to the site and there's, say, a layer of sand and we try and get a sample of that sand, well, in sampling it, we may change its density, right? We'll move the particles around relative to each other. That's going to change the strength, stiffness, compressibility of the sand. Usually it will make it weaker, right? Because you have the sand particles all oriented in a certain way, maybe they're a little bit cemented together. You go and destroy all that. When you sample it, bring it back to the lab, you can't measure the non-index properties like strength, stiffness, and compressibility on those lab samples because they've already been disturbed. So what we're going to focus on here is largely index properties. We will bring in water content for these phase relations. Now there are two tests that we'll look at specifically for soil classification also later in a different lecture. That's the grain size distribution. So what's the percent of particles larger than a certain diameter? And then the Atterberg limits. And that's a test that was invented by an agricultural soil scientist actually trying to figure out if the soil would stick to the plow. So if you make it too wet and it's too sticky, it may be hard to go and drag the plow through it. And we kind of adopted those sets of guidelines to classify soil behavior. So it's an interesting set of tests. All right, so let's talk first about phase relationships. And this will be a big focus of your first homework assignment. So phase relations are basically a way for us to represent the relative amounts of the different phases within the soil. So I've drawn this little sketch here, but let me go to this one from the book, which is a little bit clearer and cleaner. So here's what the soil might actually look like if you could get down there and take a little bit of soil, look at it under a microscope or something like that, you would have the, let's see, the solid particles here with the S. Those are the actual sand particles or silt particles or whatever they are. Then you would have zones that are filled with water, like that zone right there, all of that, those little hatch zones. That's all filled up with water. And then you would also maybe have some air bubbles. So the A's are just little air bubbles in the soil. So it's a three-phase material. You've got three different types of phases kind of all together here. So what we do with this is organize it in a way that allows us to derive the ratios between various amounts of solids and air. And we do those amounts based both on mass and based on volume, right? So we have to know the density of the solids, water, and air. We assume the density is 0. So let's go and look at what the phase diagram looks like. So this is a way for us to organize that sort of more complicated structure of the soil into a sort of a vertical diagram here so that we can do these calculations easily. So what we do first is represent the solid part using a rectangle along the bottom, and then we have the water, right, and then the air is on top. So we don't make any claims that the soil actually consists of soil, this should say solid, not soil. I think that that's kind of a mistake in the textbook. The soil is the whole phase diagram. This is the solid, so I would cross that out. Maybe I'll even do that here. Let's see. I can cross it out. Let me change the thickness of this pen so that, oh, here I have it there, and I'll just put solid. There we go. Okay, so when you draw your phase diagrams, you should write solid on the bottom, not soil. All right, so we're not making a claim that you have all of the solid part on the bottom, and then the water, and then the air. This is an abstraction of what the soil actually looks like, which is much more complicated. All right, and then what we do is divide the phase diagram into the volume side over here and the mass side over there. So the V sub S, that's the volume of solids, VW is volume of water, and VA is volume of air, right? And similarly, you have MS, it's the mass of solids, and MW, the mass of water. The mass of air we assume to be equal to 0, right? So the air is just has such a small mass, we don't have to include it in our phase diagram. Okay, and then we have some other volumes and masses that we'll talk about. One is the total mass right here, right? That's just the mass of water plus the mass of solids. And then we also have the total volume. That's the volume of all three components together. Pretty straightforward. Then another really important quantity for us is the volume of voids. And the voids are any space that is not solid, so either the water or the air. And the voids could presumably either be filled with water or filled with air. All you have to do is change the water content, right? If you keep the solid particles all in the same orientation and you replace the air with water, you would have changed the phase diagram, but you would not have changed the volume of voids. So that becomes a really important quantity for us to think about and work with. All right, so what you'll want to do when you're starting out with phase diagrams is always make the sketch and then start putting in numbers for the things that you know and then solving for the things that you don't know. But before we get to that stage, that'll be the next lecture, I just want to talk about some of the quantities that we calculate that have physical meaning for us based on these masses and volumes of the individual components. So first is the void ratio, and we call that E, lowercase e, and it's equal to the volume of voids divided by the volume of solids. So again, if we go back up here, it's the volume of voids, the volume of air plus water, divided by the volume of solids here, right? And so that's the void ratio, very important quantity. High void ratio means that the soil is pretty loose. Low void ratio means that it's pretty dense. And it's expressed as a decimal rather than as a percentage. And the reason is that its range can be anywhere from 0 to infinity. So if you had a bunch of perfect cubes of solid particles all stacked perfectly on top of each other where there's no gaps in between, then the void ratio would be 0, right? There's no void space in there. Very dense material. On the other hand, if you took 1 grain of sand and dropped it into a bucket of water, I guess you could argue that's not really soil, it's a bucket of water with a sand grain in it. But we could still make a phase diagram for that, right? And in that case, the volume of solids would be very, very small, like maybe way down here, and the volume of voids would be very big. So if you take that ratio, volume of voids to volume of solids, it can go bigger than 1, it can go up to infinity. Okay, then there's another concept called porosity that's related to void ratio, and we use lowercase n for porosity. And it's equal to the volume of voids divided by the total volume. Okay, now in this case, this is represented as a percentage, right? Because if we take that single grain of sand, drop it in a bucket of water, now the volume of voids and the total volume are pretty much the same, right? And so you get 1 for the porosity. Similarly, you still get 0 if you have the cubes, the perfect cubes all stacked on top of each other. So the porosity varies from 0 to 1, traditionally expressed as a percentage, 0 to 100%. There is a direct relationship between porosity and void ratio. So you can start doing a little bit of algebra here. The total volume is the volume of solids plus the volume of voids. So if you plug this in up here, you can get this expression for porosity. And then if you divide the top and bottom by the volume of solids, you get E on the top and an E in the bottom, and so you get N is equal to E over 1 plus E. Or alternatively, if you solve for E, void ratio is N over 1 minus N. Okay, so if you know one of these things, you can directly easily solve for the other one. All right, the next quantity that's important for us is degree of saturation. And this is a measure of what percentage of the void space is filled up with water. So it's the volume of water divided by the volume of voids. If the soil is totally bone dry, like you go to the desert and just dig up some sand, there's no water in it, then the degree of saturation is 0. Okay, if you go to the ocean and you look at the sand that's underwater, all of the void space is probably filled with water. There might be a few air bubbles still trapped in there, but generally when soil is submerged for a long time, it's fully saturated. So anyway, that's the degree of saturation. And it's usually represented as a percentage. So totally dry is 0%, fully saturated is 100%. Now when we start talking about soil mechanics, we're going to do either fully dry or fully saturated soil. But most of the time, soil is partially saturated, right? S is between 0 and 100%. You have a mix of water and air in the void space, and that creates some features of behavior that are a little bit challenging for us to deal with. And we'll talk about that later. But anyway, it's just interesting that we start with these two extremes when we go into soil mechanics. All right, another important one is water content. So the water content is the mass of water divided by the mass of solids. So what you do, this is a common thing that we measure in the laboratory. You take some soil that has a mix of solid particles and water, you measure its mass, then you put it in the oven and evaporate out all the water and measure the mass again. And now you know the mass of solids and the mass of water, so you can calculate the water content. The water content lies in the range of 0 to infinity. So it's represented in decimal form, not as a percentage, although oftentimes it is represented as a percentage, actually, but it can be bigger than 100%. I've tested peat soil from the Sacramento-San Joaquin Delta that has a water content of 1,500%, right? So that's a very high water content. The actual W value in that case would be 15, right? Okay, so here's an example calculation for water content. So what you do is you put the wet soil in a dish, and you have to know the mass of that dish. So for example, let's say we measure 462 grams of wet soil with the dish together on the scale. We usually don't just put soil directly on the scale. We put it in a little evaporating dish first. Okay, then we put it in the oven, let it dry for a day, and then we measure the mass again, and it's 364 grams. So the mass of water is simply the difference between these two. You just get 98 grams. And then let's say we know that the mass of the dish is 39 grams. You can measure just the dish by itself. So the mass of dry soil is this number minus this number. You get 325 grams. And then the water content is simply the mass of water divided by the mass of solids, and you get 30.2% in this case. Okay, now density relationships are going to be really important for us. And let me go back to the phase diagram and I'll kind of explain why. So we have a volume side here, and we have a mass side of the phase diagram. Sometimes we'll know some of these masses and maybe some of these volumes, and we have to solve for other ones in order to fully define the phase diagram. Well, the way that we get from one side to the other is using density, right? If we know the density of the solids and we know the mass of solids, then we can calculate the volume of solids. So these density relationships here become really important for us. So let's talk about some different densities that we use. Okay, one is just the total density. It's the total mass divided by the total volume. Sometimes it's also called the wet density or moist density. I like to just use total density. Another one is the density of solids, rho sub s. It's ms over vs. That's just the density of the solid particles themselves. And sometimes what we'll do is represent that as a multiplier on the unit weight of water. Okay, so solid particles are denser than water. So what we'll define is this specific gravity term, G sub s. And that's the ratio of the density of the solid particles to the density of water. It's a scalar number. It's typically about 2.65 to 2.8 for the soils that are typical soils. This is not organic soil, or this would be inorganic sands and silts and clays. Specific gravity range is over a fairly narrow range, right? So a lot of the time we don't even take the time to measure this. We just assume it's 2.7, for example, and move forward there. Okay, and then there's also the density of water. Usually we just treat this as a constant number, right? It's 1 megagram per meter cubed, or that's in density, mass per volume. Sometimes we do unit weight too, which would be 9.81 kilonewtons per meter cubed. So you would, multiply by the acceleration of gravity to get force measurements. And that assumes that the acceleration of gravity is a constant, 9.81 meters per second squared. All right, then there's also dry density. Okay, this is a very useful quantity when we go to compaction. We'll come back to the concept of dry density later in the quarter. So its symbol is rho sub d. It's the mass of solids divided by the total volume. So essentially what you're measuring is how tightly packed are the solid particles. And the reason why dry density is important is that it's the solid particles that are responsible for carrying loads and stresses. So if we put them very dense, the soil is stronger and stiffer. It's easier for the soil to take that load without deforming a lot. So we want to have a high dry density for the soil. Total density is not so much directly related to strength and deformability, because you can change the total density quite a bit by just adjusting the water content, right? If you have totally dry sand and it's pretty dense and strong, and then you fill up the void space with water, the total density is going to change quite a bit because you're replacing air with water, but the strength and stiffness doesn't really change because the dry density hasn't changed. So that's why we use dry density for compaction, because we want to get the solid particles tightly packed to make the soil stiff and strong. Okay, then there's also the saturated density. And the saturated density is kind of like you're asking the question, what would be the total density if the soil were to be fully saturated? So if you took all of the air and replaced it with water, what would be the total density? And I have this equation here. I'm not sure that this equation is actually the most representative one, so I'm going to write in a new equation here. Hopefully I can get this right. I'm kind of going on the fly here. So this equation is correct as long as the soil is fully saturated, but you have to do a calculation in order to get it there. So let's write the actual equation, right? So you have rho sat. Actually, that pen's a little too thick. Let me pick the thinner one. There we go. rho sat is equal to ms plus mw plus rho w VA divided by VT. So let me explain what I'm doing here. I think this equation that I just wrote makes it a little bit clearer. What I'm doing is saying we have a phase diagram, there's some mass of solids, there's some mass of water, and then there's some volume of air. So if we go back up here to our phase diagram drawing, right, we have a true three-phase medium. So the new equation does correspond exactly to this one. What we're saying now is, what if you took this air away and replaced it with water, right? So you keep the same total volume, you're just changing the degree of saturation to be 100%. If you did that, the additional mass would be equal to the volume of air times the density of water, right? Because you're replacing air with water. So here we go. That's why I've written this equation here. Volume of air times the density of water would be like the additional mass of water you would get if you were to make the soil fully saturated. So I think that this equation is better. I'll be sure to upload this version of the PDF file to the course website so that you have this new equation. Maybe I will put an X through this one. There we go. Okay, and then there's one more concept that's important before we end, and that's the buoyant density. So the buoyant density is important when we get to computing effective stress, which is like the key concept in soil mechanics. So we're not quite there yet. We'll get to that in the next section of the course. But I wanted to introduce buoyant density here just to explain to you what it means. It's defined as the saturated density minus the density of water. So basically it's like how much of the soil is pushing down if the soil's floating in water, or if it's fully saturated, right? There's standing water there. And what I use to describe this is that when I go swimming with my kids, one thing they like to do is hold me up and walk around, because in the pool they can hold my body weight, right? Because the water is holding most of my body weight. They're just holding kind of the difference between my weight and the density of water, well, and any part of my body that's up above the water. So they feel really strong, they can carry me around. There's no chance they could carry me around if it's in air, right? And way too heavy, I would probably break them. So the buoyant density is a measure of how much weight my kids have to hold when we're in the water together. Because some of the weight is taken by water, they're holding the rest, which would be like the buoyant density times my volume. That would be the sort of the buoyant mass. So anyway, the meaning is discussed when we talk about effective stress. It'll make a lot more sense when we get there, but right now just know that the symbol for it is rho prime, and then it's defined as the saturated unit weight minus the unit weight of water.